as the world celebrates the all-clear on 3i Atlas, the third interstellar traveller in history. Another unsettling act is unfolding in the shadows, and we just noticed it. A comet, surging with outbursts, is wandering closer to Earth's lane than comfort should allow. It slipped past our telescopes until the sun itself gave it away, and on October 20th, 2025, just 8 days from now, it will reach its closest approach to Earth. What does that mean for us here on Earth? Is this the real threat? Stay with me until the end, and you'll see why the real threat was never the comet in the news, but the one we almost didn't see at all. If these mysteries have you hooked the way they have me, make sure to hit like and subscribe so you don't miss a single update as this unfolds in real time. Drop a comment with where you're tuning in from, what time it is there, and whether you believe we're getting the full truth about these world-changing discoveries. And if you want to help this community grow, share this video on X, Facebook, Reddit, or even just in your group chats. You're the reason we can keep chasing stories like this, so thank you for having our back. Part 1. The title claim right now. Everyone is screaming about 3i Atlas. The headlines call it mysterious, the social feeds light up with theories, and astronomers bend over backward to reassure us it poses no danger. They are right. 3i Atlas, that interstellar wanderer from beyond our solar neighbourhood, will cruise past Earth at a comfortable 1.8 astronomical units, which translates to roughly 167 million kilometres. NASA has said it plainly. No threat. The orbit stays far from us, a celestial sightseer that will glide by and vanish back into the void. So why are we obsessed with it? Because it came from somewhere else. Because the word interstellar carries a kind of magic that makes us forget the practical. We love the exotic visitor, the stranger at the door. We forget to check who is already in the house. While the world watches 3i Atlas, another object is sliding into our neighbourhood. Comet C/2025 R2, designated SWAN after the instrument that found it, is closing in. On October 20th, 2025, just 8 days from now, it will reach its closest approach to Earth. Not 1.8 astronomical units, not even 0.2606 astronomical units, roughly 39 million kilometres. That is closer than you think. That is closer than we usually like uninvited guests to get. Let me give you the shape of this thing. R2 was discovered late in September 2025 by an amateur astronomer named Vladimir Bezugli, who was scanning data from a solar wind instrument aboard the Soho spacecraft. He was not looking through a telescope. He was watching hydrogen emissions glow in ultraviolet light. That is not how we usually find comets. Normally, ground-based optical surveys sweep the sky, catching faint dots of reflected sunlight. But R2 was invisible to them. It had been hiding in the sun's glare, too close in angular separation for Earth-based telescopes to see. The phenomenon is called the Holecek, or Hulich blind spot effect. Objects in that zone are ghosts. They exist, but we cannot perceive them until they emerge. R2 emerged only after it had already passed perihelion, its closest point to the Sun, on September 12th, 2025. By the time we spotted it, it was already on its way out heading toward us. Perihelion distance was about 0.5 astronomical units, roughly 75 million kilometres from the Sun. That is close enough to roast volatiles off its surface, to trigger outbursts to destabilise structure, and it did. In late September, observers recorded a sudden brightening. The comet jumped in magnitude to around 5.9 or 5.6 depending on the report. Its coma, the cloud of gas and dust surrounding the nucleus, swelled. Photographs showed a greenish halo, the signature of diatomic carbon and cyanogene radicals fluorescing under solar, ultraviolet. The tail stretched across a few degrees of sky, visible through binoculars if you knew where to look. But here is the thing. We still do not know the size of the nucleus. We do not know its rotation state. We do not know if it has fractured, or if it will fracture. Comets are volatile beasts. They can shed chunks, split into fragments, spray debris fields along their orbits, and if R2 does any of that, those fragments will diverge slightly from the parent trajectory. They will spread out. They will form a cloud of potential intersections with Earth's orbit. The minimum orbit intersection distance, or MOID, between R2 and Earth is roughly 0.048 astronomical units. That is about 7 million kilometres. In cosmic terms, that is a hair. That is the gap between safe and maybe not so safe, depending on what happens next. Now, I am not here to tell you that R2 is going to hit us. Current orbital solutions say it will not. But I am here to tell you that our inability to see it earlier is the real risk. We have built a detection system that works beautifully for objects in the right part of the sky, at the right brightness, at the right time. But if an object hides in the sun's glare or arrives from an unexpected angle, or brightens suddenly after we have already looked away, we miss it. We missed R2 until it was practically on top of us. How many others have we missed entirely? This is not about panic. Panic is useless. This is about paying attention to what almost always escapes our view. It is about recognizing that the scariest objects are not the ones making headlines. They are the ones we do not see until it is too late. 3i Atlas is a sideshow. It is the magician's hand waving in the air while the trick happens somewhere else. R2 is the trick. So here is what we are going to do. First, we will dismantle the 3i Atlas distraction and show you why it is safe. Then we will dive into everything we know and everything we do not know about R2. We will explore the speculative risk scenarios, the dust trails, the fragments, the meteoroid swarms. We will compare this to past near misses that we barely saw, objects that slipped past our defences with only days or hours of warning. And we will end with what you should watch, what you should demand from the institutions that are supposed to keep track of these things, and what happens when the detection system fails. Because it does fail, more often than you think, and when it does, the thing that sneaks through is not always the one you were watching. Part 2. Discovery mechanics. Why Swan found it, and ground surveys didn't. Comets are usually spotted by optical sky surveys. Telescopes scan the night, looking for faint dots that move against the background stars. The dots brighten as they approach the sun, their ice sublimates, and they grow tails. We have been doing this for centuries. It is a reliable method, except when it's not. Comet C/2025 R2 was not found by an optical telescope. It was discovered by a hydrogen emission detector aboard a spacecraft orbiting the Sun. The instrument is called SWAN, which stands for Solar Wind Anisotropies. It is part of the SOHO mission, the Solar and Heliospheric Observatory, launched in 1995. SWAN was designed to image the solar wind by detecting hydrogen, lime and alpha emissions in the ultraviolet spectrum. Hydrogen glows at a specific wavelength, 121.6 nanometers, invisible to the human eye but bright in UV. When comets release water vapor through sublimation, that vapor breaks down into hydrogen and oxygen. The hydrogen spreads out in a massive cloud around the comet, much larger than the visible coma. SWAN can see that cloud from millions of kilometers away, even when optical telescopes see nothing. This is not a new trick. SOHO/SWAN has discovered thousands of comets over its operational life, most of them small sun-grazing objects that plunge into the solar atmosphere and vaporize. But R2 is not a sun grazer. It is a visitor from the outer solar system, likely the Oort cloud, making a close pass by the sun and then heading back out. What made it invisible to ground surveys was its position. It was too close to the sun in the sky. The angular separation was too small. Telescopes on Earth cannot look directly at the sun without being blinded. There is a zone around the sun, a cone of invisibility, where objects simply vanish from our view. Astronomers call this the Holetschek effect or the Hulish blind spot, depending on which historical figure you prefer to credit. The principle is the same. Objects in that zone are ghosts. R2 spent its perihelion passage in that zone. It swung around the sun on September 12, 2025, at a distance of roughly 0.5 astronomical units, about 75 million kilometers. For weeks before and after, it was invisible to optical surveys. By the time it emerged from the glare, it had already passed perihelion and was heading outward toward Earth's neighborhood. That is when Vladimir Bezugli, an amateur astronomer spotted it in SWAN data. He was scanning archived ultraviolet frames looking for the telltale glow of hydrogen. He found a moving blob, a diffuse cloud that shifted position over time. He flagged it. Other observers checked. Optical confirmation followed. The comet was real. But by then, we had lost weeks of observation time. We had no data on its pre-perihelion behaviour. We did not know how it brightened, how its orbit evolved, whether it had already started fragmenting. Detection bias is a cruel filter. Optical surveys have minimum magnitude limits, gaps in sky coverage, weather interruptions and glare zones. Hydrogen UV instruments like SWAN have different sensitivities, different blind spots. They can catch comets that optical telescopes miss, but they are not designed for comprehensive sky surveys. They are specialised tools, and specialised tools catch specialised things. The consequences of late detection are serious. Orbit uncertainties are higher when you have fewer observations. You need time to refine the trajectory, to measure perturbations, to account for non-gravitational forces like outgassing. R2 was discovered late. Its orbit was uncertain. Even now, weeks later, there are still margins of error. We know roughly where it is going, but roughly is not precisely. And in orbital mechanics, precision is everything. We also missed the early activity. Comets often outburst near perihelion, when solar heating triggers explosive release of volatiles. If R2 did that, we did not see it. We do not know if it shed large fragments during that time. We do not know if its nucleus cracked. We do not know its rotation state, which affects how it spins and wobbles under asymmetric outgassing forces. All of that information is gone. We are flying blind, trying to predict the behaviour of an object we only started watching halfway through its show. This is not a failure of individual astronomers. This is a structural limitation of our detection network. We have optimised for certain kinds of objects in certain parts of the sky. When something falls outside those parameters, we miss it. And we miss it completely until an amateur astronomer with access to a spacecraft instrument happens to notice a hydrogen glow in archived data. How many other comets have we missed? How many are passing through the solar system right now, invisible because they are in the wrong place at the wrong time? We do not know. We cannot know. That is the problem. Next, we're going to look at what R2 has actually done since discovery, the outbursts, the oddities, the structural weirdness that makes this comet more than just another icy rock. Part 3. What R2 has actually done. Let me walk you through the timeline. On September 11th, 2025, Vladimir Berzugli identified a moving hydrogen source in SWAN imagery. The object was designated C/2025-R2, with the R indicating the half-month of discovery and the 2 indicating it was the second comet found in that period. Optical confirmation came quickly. Ground-based observers turned their telescopes toward the coordinates and saw it. A fuzzy patch, a coma glowing faintly in the pre-dawn sky. The comet had passed perihelion the day before, on September 12th, at a solar distance of roughly 0.50347 astronomical units. That is close. Close enough to sublimate water ice, carbon dioxide, methane, ammonia, all the volatiles that comets carry. Close enough to trigger activity, and activity happened. In late September, observers reported a sudden brightening. The comet jumped in apparent magnitude, some estimates putting it at 5.9, others at 5.6. Magnitude is logarithmic, so even a small numerical change means a significant increase in brightness. The coma expanded. Photographs showed a greenish halo surrounding the nucleus, the signature of diatomic carbon molecules glowing under ultraviolet light. This is common in comets. Carbon compounds sublimate from the nucleus, get ionized by solar radiation and fluoresce green. It looks alien, but it is just chemistry. The tail developed asymmetries. Some images showed streamers, narrow jets of material pointing away from the sun. This suggests localized outgassing, probably from active vents on the nuclear surface. Comets are not uniform. They are patchworks of ice and rock, with some areas more volatile rich than others. As the nucleus rotates, different vents turn toward the Sun, triggering bursts of activity. The result is a tail that shifts shape, that pulses, that sometimes splits into multiple streams. R2 showed all of this. Observers also noted heavy dust retention. Normally, solar radiation pressure pushes small dust grains away from the comet, forming a smooth tail. But if the grains are large or sticky, they lag behind, creating a diffuse cloud that spreads slowly. R2 seemed to be producing a lot of large grains. This has implications. Large grains mean the nucleus is shedding chunks, possibly fragments, possibly pieces of the surface cracking off under thermal stress. If those chunks are big enough, they might survive as independent objects, each with its own trajectory, and those trajectories might diverge from the parent comet, spreading a debris field across space. One particularly striking image appeared on the Astronomy Picture of the Day website on September 18th, 2025. It showed R2's greenish coma against the twilight sky, with the tail extending upward, away from the glare of the hidden sun. The comet was still close to the horizon, difficult to observe, but unmistakable. Astrophotographers caught it, some using binoculars, some using small telescopes. Reports describe the tail as several degrees long, a ghostly ribbon stretching across the sky. But here is the thing. Brightness predictions for comets are notoriously unreliable. Comets do not follow simple rules. They outburst, they fade, they fragment. Their brightness depends on how much surface area is actively sublimating, which depends on the nucleus size, composition, rotation, and solar heating. We can make educated guesses, but comets love to surprise us. R2 has been predicted to reach magnitude 4 under optimal conditions, which would make it easily visible to the naked eye from a dark site. Other predictions are more conservative, suggesting it will stay around magnitude 6, requiring binoculars. As of October 10th, 2025, the reported magnitude is about 6.7, which puts it just below naked eye visibility. Whether it brightens further depends on whether it outbursts again, and we do not know if it will. The nucleus itself remains unresolved. Telescopes see only the coma, the glowing envelope of gas and dust. The solid core is buried inside, too small and too faint to distinguish. We do not know its size. Estimates based on brightness and activity suggest something on the order of a few kilometers in diameter, but that is a guess. We do not know its shape. We do not know if it is a single object or a cluster of fragments loosely bound together. We do not know if it has already split. Some comets fracture quietly, shedding pieces without dramatic outbursts. You only notice later when you image the coma at high resolution and see multiple condensations, multiple nuclei. Speculative but worth noting. The outburst in late September suggests internal volatile reservoirs. Something inside the comet built up pressure and released violently. That could be carbon monoxide ice, which sublimates explosively. It could be subsurface pockets of water ice suddenly exposed to sunlight. It could be structural failure, a crack opening and venting gas. Whatever it was, it happened once. It could happen again. And if it happens at the wrong time, if the comet is close to Earth when it fragments, those pieces will spread into a debris cloud, a cloud we might fly through. Next, we're going to talk numbers, the hard orbital data, the distances, the speeds, the geometry that determines whether this is curiosity or a concern. Part 4. Hard numbers and orbital reality check. Let me give you the geometry. Comet C/2025R2 orbits the Sun on a nearly parabolic trajectory. Its orbital eccentricity is 0.9993699, which is as close to 1 as you can get without actually being 1. An eccentricity of exactly 1 means a parabola, an open curve, an object that comes in from infinity and goes back out to infinity. An eccentricity slightly less than 1 means an extremely elongated ellipse, a trajectory that takes tens of thousands of years to complete. R2's orbit has a semi-major axis of roughly 798 astronomical units. That means the farthest point of its orbit, the aphelion, is somewhere far beyond the Kuiper belt, deep into the Oort cloud. The orbital period is estimated at 22,554 years. This comet last visited the inner solar system during the late Paleolithic, when humans were painting caves and hunting mammoths. The inclination of the orbit is about 4.47 degrees. That is the angle between the comet's orbital plane and the ecliptic, the plane of Earth's orbit. 4.47 degrees is low. Most comets from the Oort cloud arrive at steep inclinations, diving in from random angles. R2 is almost coplanar with the planets. That makes its trajectory easier to predict, but it also means it spends more time near the ecliptic plane, where Earth orbits. That increases the chance of close encounters. Perihelion, the closest point to the Sun, occurred on September 12th, 2025, at a distance of 0.50347 astronomical units. That is about 75 million kilometres, just inside the orbit of Venus. At that distance, solar heating is intense. Surface temperatures can reach several hundred degrees Celsius. Water ice sublimates rapidly. Volatiles outgas. The nucleus sheds dust and gas at a furious rate. This is when comets brighten, when they become spectacular, when they also become unstable. Now we move outward. R2 is travelling away from the Sun, but its trajectory crosses Earth's orbital path. On October 20th, 2025, the comet will reach its closest approach to Earth. The distance will be 0.26065 astronomical units, which translates to approximately 38,992,517 kilometres. That is about 100 times the distance to the Moon. In human terms, that sounds far. In cosmic terms, it is a near miss. But the key number is the MOD, the minimum orbit intersection distance. This is the smallest possible gap between Earth's orbit and the comet's orbit, calculated geometrically without regard to timing. For R2, the MOID is about 0.048 astronomical units, roughly 7 million kilometres. That means if you drew both orbits in space and measured the shortest distance between them, you would get 7 million kilometres. That is the gap. If the comet and Earth were at the wrong place at the wrong time, that gap could shrink to 0. But they are not. The current orbital solution shows that on October 20th, Earth and R2 will be separated by 39 million kilometres. The comet will pass and we will be safe. The models say so. The calculations say so. NASA is not issuing warnings. There is no impact alert. So why are we still talking about this? Because orbital solutions are not perfect. They are based on observations, and observations have uncertainties. The more observations you have, the better the solution. But R2 was discovered late. We have fewer observations than we would like. The orbit is reasonably well constrained, but it is not perfectly constrained. Small perturbations, non-gravitational forces from outgassing, changes in the comet's rotation or mass distribution, all of these can shift the trajectory slightly. A shift of a few thousand kilometres might not matter for the parent nucleus, but it matters a lot if the comet has shed fragments. Fragments can diverge. If R2 is fractured, if it is split into pieces, those pieces will have slightly different velocities. Over time, they will spread out along the orbit, forming a debris stream. The larger the fragment, the less it diverges. Small fragments, dust grains, pebbles, these can spread widely. And if Earth passes through that debris stream, we will see an increase in meteor activity, maybe a meteor storm, maybe something worse. Current brightness is magnitude 6.7 as of October 10th, 2025. That is dimmer than prediction suggested, but not surprising. Comets fade as they move away from the Sun. The question is whether R2 will outburst again. If it does, if it suddenly brightens, that will signal renewed activity, possibly fragmentation, possibly a new release of volatiles, and that will change the risk profile. Visualization helps. Imagine the Sun at the centre. Earth's orbit is a circle around it, roughly 150 million kilometres in radius. R2's orbit is a stretched ellipse, coming in from the outer solar system, swinging around the Sun and then heading back out. The two orbits intersect, but not at the same time. The comet passes through the intersection point in October. Earth passes through it months later. The gap is spatial and temporal. As long as both remain true, we are safe. But comets are not predictable. They do not follow railway schedules. They wobble, they crack, they shed pieces. And pieces do not follow the parent trajectory. They drift, they spread, and sometimes they arrive when you least expect them. Next, we are going to talk about the theatre of observation, the public spectacle, the distractions, and the way media coverage shapes what we pay attention to. Part 5. The near-term theatre, viewing, meteor overlap and public distraction. October is turning into a crowded sky. Comet C/2025 R2 is approaching its closest pass to Earth, peaking around October 20th. But it is not alone. Another comet, C/2025 A6, also known as Lemon, is also brightening and becoming visible in the northern hemisphere around the same time. Two comets, both visible to amateur astronomers, both making their closest approaches within days of each other. It is a spectacle. It is rare. It is the kind of thing that gets people looking up. And then there is the Orionid meteor shower. The Orionids peak every year around October 20th to 21st, when Earth passes through the debris trail of Comet Halley. Yes, Halley, the famous one, the one that visits every 76 years. Even when Halley is far away, its trail lingers, a stream of dust and ice fragments spread along its orbit. Every October, Earth crosses that stream, and particles slam into the atmosphere at 70 kilometers per second. They burn up, creating streaks of light, meteors. The Orionids typically produce 10 to 20 meteors per hour at peak, sometimes more. It is not a major storm, but it is reliable. So on the night of October 20th, 2025, you will have two comets visible in the sky, and a meteor shower at peak activity. The sky will be busy. The media coverage will be busy. Astronomy enthusiasts will flood social media with photos. News outlets will run stories about the celestial show. It is a perfect moment for public engagement. It is also a perfect moment for distraction. Because while everyone is watching the Orionids, while astrophotographers are capturing the two comets, while the headlines talk about the beauty and wonder of the cosmos, very few people will be asking the harder questions. How close is R2 really? What is its uncertainty margin? Has it fragmented? Are we tracking debris? What happens if something unexpected occurs? The Washington Post covered the twin comet event, noting that both R2 and Lemon would be visible to observers with binoculars or small telescopes. They emphasized the rarity, the beauty, the chance to see two comets at once. They did not emphasize the proximity. They did not mention the moid. They did not discuss fragmentation risk. That is not a criticism. It is just the nature of public science communication. Spectacle sells. Risk assessment does not. And then there is 3i Atlas, the interstellar interloper, still dominating headlines even though it will pass at 1.8 astronomical units, a safe distance by any measure. The media loves 3i Atlas because it is mysterious. It came from another star system. It is red, or maybe green, depending on which observation you trust. It changes colour, or seems to, which is weird. Asteroids do not usually do that. It has sparked speculation about artificial origins, about alien probes, about messages encoded in its trajectory. None of that is likely, but it is exciting. It is clickable. It is the kind of story that gets shared. Meanwhile, R2, the closer visitor, the one with an uncertain orbit and a history of outbursts, gets quieter coverage. It is less exotic. It is a solar system native, probably from the Oort cloud. Nothing interstellar about it. It is just another comet. Except it is not. It is a comet we did not see until it was almost on top of us. It is a comet that hid in the sun's glare and emerged only after perihelion. It is a comet that might have fragmented and might still fragment. It is a comet whose mod is 7 million kilometres, which is uncomfortably small. Public perception is shaped by novelty. 3I Atlas is novel, R2 is not. So 3I Atlas gets the headlines, and R2 becomes a footnote. But footnotes can be dangerous. Footnotes can hide the things that matter. Behavioural caveats are necessary here. Comets are not reliable performers. They brighten unpredictably. They fade unpredictably. They fragment without warning. Predictions are guesses informed by past behaviour, but every comet is different. R2 might brighten to magnitude 4 and become a naked eye spectacle. It might fade to magnitude 8 and disappear from view. It might split into fragments and create a debris field. It might do nothing at all and quietly slip back into the outer solar system, forgotten in a year. We do not know. What we do know is that this is not an impact alert. The current orbital solution says R2 will miss Earth by 39 million kilometres. That is not close enough for a collision. But it is close enough for other things. Close enough for debris interactions. Close enough for meteor flux increases. Close enough that if the comet fragments unexpectedly, pieces might diverge into Earth-crossing trajectories. This is the nature of cosmic risk. It is not binary. It is not safe or doomed. It is probabilistic, uncertain, layered with contingencies. And our detection system, the network of telescopes and surveys that we trust to warn us, is not designed to handle contingencies. It is designed to handle predictable objects on stable orbits. When something unpredictable happens, when an object hides in the glare or brightens suddenly or sheds fragments, the system struggles, and we struggle with it. Next, we go deeper. We're going to look at past near misses, at asteroids that flew past Earth with almost no warning, at the detection failures that happen more often than anyone wants to admit. Part 6. Case Studies. Asteroids we only discovered just before or after their flybys. In early 2025, an asteroid designated 2025 TF passed within approximately 400 kilometres of Earth's surface. 400 kilometres. That is closer than the International Space Station. That is closer than most satellites. That is inside the orbital altitude of many space assets, and we did not see it coming until it was almost there. 2025 TF is small, probably only a few metres across. At that size, even if it had hit the atmosphere, it would have burned up, creating a bright fireball but no ground damage. The Chelyabinsk meteor in 2013 was about 17 to 20 metres in diameter, and it exploded in the air with a force of several hundred kilotons of TNT. It shattered windows, injured over 1,000 people but left no crater. 2025 TF was smaller. It would have been a light show, nothing more. But the point is not the size. The point is the detection latency. We did not see it until it was practically on top of us. It passed over Antarctica, one of the most remote regions on Earth, where very few people were watching. If it had arrived a few hours earlier or later, if its trajectory had been slightly different, it might have passed over a populated area. And we would have had no warning. This is not an isolated case. In recent years, several small asteroids have been discovered only days, hours, or even minutes before their closest approach. Some were found after they had already passed. They flew by Earth, invisible to our surveys, and we only spotted them on the way out. This happens because our detection network has limits. Telescopes have minimum brightness thresholds. Small objects are faint. If they approach from the direction of the sun, they are invisible. If they arrive at high speed, they cross the sky too, quickly for automated surveys to catch them. If they are dark, low albedo, they reflect very little sunlight and blend into the background. Detection bias is not just a theoretical problem. It is a practical, observable failure mode. We miss things. We miss them often, and we usually only find out we missed them when someone happens to look at the right patch of sky at the right time and notices something moving. The consequences are more serious than you might think. Yes, most small asteroids burn up harmlessly, but not all. And even a small object, if it hits the right target, can cause catastrophic damage. A few meters of rock hitting a satellite at orbital velocity would destroy it instantly. A collision with the International Space Station would be fatal. A strike on a city, even from a small impactor, could level buildings and kill thousands. The atmosphere is a shield, but it is not a perfect shield. Objects larger than about 20 meters can survive to the ground. Objects smaller than that can still produce damaging airbursts. And then there is the debris issue. When an asteroid breaks up in the atmosphere, It scatters fragments over a wide area. Most fragments are small, but some can be large enough to cause damage. If the breakup occurs over a densely populated region, those fragments become projectiles. The Chelyabinsk event scattered meteorites over hundreds of square kilometres. People collected them as souvenirs. But if the object had been larger, or if the breakup had occurred at a lower altitude, the fragments would have been more dangerous. Now scale this up. Instead of a single small asteroid, imagine a debris cloud from a fragmenting comet. Instead of a few meters of rock, imagine hundreds or thousands of pieces, ranging from dust grains to boulders, spread along the orbit. Instead of a single point of impact, imagine a diffuse threat, a statistical hazard where any one piece is unlikely to hit, but the aggregate probability is non-negligible. That is what happens when comets fragment. They do not create a single bullet, they create a shotgun blast. R2 has a emoid of 7 million kilometres. That is the gap between Earth's orbit and the comet's orbit. If the comet fragments, if pieces spread along the orbit, some of those pieces might drift closer. Not to zero, not to impact, but closer. Close enough that the statistical probability shifts from negligible to small but non-zero. And small but non-zero is enough to make risk analysts nervous. This is the lesson from 2025 TF and others like it. Detection latency is real. We do not see everything. We do not see most things, if they are small or fast or coming from the wrong direction. The asteroids we catch are the ones that play by the rules, the ones that arrive on predictable trajectories from predictable directions at predictable times. The ones that do not play by the rules, those are the ones that scare us, because those are the ones we miss. Next, we are going to talk about how comets do not have to hit to be dangerous, how debris and dust trails create hazards that persist long after the parent object has moved on. Part 7. Comet fragmentation and dust trail hazard. Realistic speculative scenarios. Even if a comet misses, its debris can bite. Let me explain how that works. Comets are not solid rocks. They are loosely bound aggregates of ice, dust, rock, and organic compounds, held together by weak gravity and surface tension. They are fragile. When they approach the sun, thermal stress cracks them. Outgassing creates pressure that splits them. Tidal forces, if they get close enough to a massive body, pull them apart. Sometimes they fracture quietly, shedding small pieces. Sometimes they shatter spectacularly, breaking into dozens of fragments. Comet Shoemaker-Levy 9 is the famous example. In 1992, it passed too close to Jupiter and was torn apart by tidal forces. The fragments, more than 20 of them, spread out along the orbit. 2 years later, they slammed into Jupiter one by one, creating massive explosions visible from Earth. Each impact released energy equivalent to millions of nuclear bombs. The scars in Jupiter's atmosphere persisted for months. It was spectacular. It was also a demonstration of how fragile comets are and how dangerous their fragments can be. Another example, Comet 73P/Schwarzmann-Wachmann. This one has fragmented multiple times. In 1995, it broke into several pieces. In 2006, it fragmented again, this time into dozens of smaller chunks. Observers watched in real time as the comet disintegrated, each fragment developing its own coma, its own tail. The fragments continued to spread, each following a slightly different trajectory. Over time, they formed a debris stream, a river of ice and dust flowing along the original orbit. Earth has passed through parts of that stream. The result was a brief increase in meteor activity, nothing catastrophic, but noticeable. Now apply this to R2. The comet has already outburst at least once, which suggests internal instability. If it fragments, the pieces will diverge. The divergence rate depends on the relative velocities, which depend on the energy of the fragmentation event. A gentle split produces slow separation. A violent explosion produces fast separation. Either way, over time, the fragments spread out, and so does the dust they produce. Dust is the real hazard. Every comet sheds dust continuously as it sublimates. The dust particles are tiny, microns to millimeters in size, but they are moving at tens of kilometers per second. At those speeds, even a grain of sand carries enormous kinetic energy. If a dust particle hits a spacecraft, it can puncture the hull. If it hits a satellite, it can damage solar panels, sensors, or communication equipment. If it hits a human on a spacewalk, it can be fatal. The International Space Station, for example, is shielded against micrometeoroids. The shields are multi-layered, designed to vaporize incoming particles before they penetrate the hull, but the shields are not perfect. Large particles, or particles arriving at unusual angles, can get through. ISS has been hit multiple times. Most strikes cause minor damage, but some have required repairs. A dense meteoroid stream, the kind produced by a fragmenting comet, increases the risk significantly. Now consider the geometry. R2's amoid is 7 million kilometers. That is the minimum distance between the comet's orbit and Earth's orbit. If the comet fragments, and if the fragments spread along the orbit, some of them might drift closer to Earth's path. Not all the way, not to zero, but closer. And if Earth passes through the debris stream at the wrong time, we might encounter a higher than usual flux of particles. That could mean an enhanced meteor shower, it could mean damage to satellites, it could mean micrometeoroid impacts on spacecraft. The probability of any individual particle hitting a specific target is low. Space is big. Targets are small, but the aggregate probability, the chance that something somewhere gets hit, is higher. And we have a lot of things in orbit now. Thousands of satellites, space stations, crewed spacecraft. All of them are potential targets. There is also the atmospheric interaction scenario. If Earth passes through a dense dust stream, even if the particles are small, the aggregate effect might be visible. High-altitude airglow could increase. Bolide activity. Bright meteors that explode in the upper atmosphere might spike. Amateur astronomers would notice. Meteor cameras would record an anomaly. It would not be catastrophic, but it would be unusual, and unusual events tend to trigger alarms. The real concern is not the dust we see, it is the fragments we do not. A boulder-sized chunk, a metre or two across, travelling at 30 kilometres per second, would be nearly invisible until it was too late. Optical surveys might catch it, but only if they happen to be looking at the right patch of sky at the right time. If the fragment approached from the direction of the sun, it would be invisible. If it had low albedo, dark surface material, it would be nearly impossible to spot. And if it hit the atmosphere over a populated area, the result would be a Chelyabinsk scale event or worse. Probability estimation is difficult here. We do not know if R2 is fragmented. We do not know if it will fragment. We do not know how many pieces it might produce or how they might spread. We do not know the size distribution, the velocity distribution, or the trajectory distribution. All we have is the parent comet's orbit and a 7 million kilometre gap between that orbit and Earth's path. Within those constraints, we can say the probability of a fragment hitting Earth is low. But low is not zero, and when the consequence of being wrong is measured in lives and infrastructure, low is not always low enough. Visualization helps again. Imagine the comet's orbit as a thread in space. Now imagine that thread fraying, splitting into dozens or hundreds of smaller threads, each one slightly different. Some threads stay close to the original path, some drift away. The cloud of threads spreads over time, forming a diffuse ribbon along the orbit. Earth's orbit is another thread, crossing the ribbon at an angle. Most of the time, Earth passes through empty space, but sometimes it crosses the ribbon, and when it does, the particles in the ribbon rain down. This is not speculation without precedent. Meteor showers are exactly this phenomenon. The Perseids, the Leonids, the Orionids, all of them are debris streams from comets. Every year Earth passes through these streams and we see meteors. Usually it is harmless. Occasionally it is spectacular. Very rarely it is dangerous. In 1833, the Leonid meteor storm produced tens of thousands of meteors per hour. Witnesses described the sky as filled with fire. If that happened today, with our satellite infrastructure, the damage would be severe. R2 is not predicted to produce a meteor storm. Its debris, if it exists, is probably too sparse. But we do not know. We cannot know until we see it, and by the time we see it, it might be too late to do anything except watch. Next, we are going to ask a bigger question. Are we seeing a surge of surprise visitors, or is this just observational bias? Is the solar system sending us more objects, or are we just finally starting to notice? Part 8. Pattern recognition. Are we seeing a surge of surprise visitors? Let me list them for you. Oumuamua arrived in October 2017, the first confirmed interstellar object detected passing through our solar system. It was strange, elongated, tumbling, accelerating in ways that did not match outgassing models. It left before we could study it properly. Then came Borisov in August 2019, the second interstellar visitor, this one clearly a comet, with a coma and a tail and composition consistent with what we expect from another star's debris. Now we have 3I Atlas, discovered in 2025, another interstellar object. This one an asteroid or comet nucleus, depending on who you ask. It changes colour. It is weird. And while the world watches 3I Atlas, R2 sneaks in from the solar system's own backyard, undetected until after perihelion. 4 objects in 8 years. Oumuamua, Borisov, 3I Atlas, R2. Different origins, different compositions, different discovery circumstances, but all of them unexpected. All of them arrived with short notice or no notice. Is this a pattern? Is this a surge? Or is this just what happens when you finally start paying attention? There are 3 hypotheses. The first is observational bias. We have better instruments now. More telescopes, more sky, surveys, more amateur astronomers with access to professional-grade data. We are looking harder, so we are finding more. The survey systems like Pan-STARRS, Atlas, and the upcoming Vera Rubin Observatory are designed to catch transient events, moving objects, anything that changes. As these systems come online and improve, the detection rate goes up. That does not mean more objects are arriving. It means we are finally seeing the objects that were always there. The second hypothesis is a real dynamical flux increase. Maybe something is perturbing the Oort cloud. Maybe a passing star, long gone, sent a wave of comets inward, and we are just now seeing the first arrivals. Maybe the solar system is passing through a region of space with higher debris density. Maybe galactic tides, the gravitational influence of the Milky Way's structure, are nudging more comets toward the inner system. This is not impossible. The Oort cloud is enormous, containing trillions of comets. A small perturbation could send thousands of them inward over the course of a few thousand years. From our perspective, trapped in our short human timescales, that would look like a sudden surge. The third hypothesis is statistical clustering, pure coincidence. Random processes produce clusters. Flip a coin 100 times and you will see streaks of heads or tails. That does not mean the coin is biased, it means randomness clumps. 4 unexpected visitors in 8 years might just be noise, a statistical fluctuation with no deeper meaning. In another 8 years, we might see none, or we might see 10. Without more data, we cannot distinguish signal from noise. Each hypothesis has evidence. Observational bias is strong. The number of known near-Earth asteroids has exploded over the past 2 decades, not because more asteroids suddenly appeared, but because we started looking for them systematically. The same is likely true for comets. SWAN has discovered thousands of comets, most of them sun gazers, simply because SWAN can see things optical telescopes cannot. As our detection network expands, so does the catalogue. But observational bias does not explain everything. Oumuamua was genuinely weird. Its elongated shape, its non-gravitational acceleration, its lack of a visible coma, all of that defied easy explanation. Some astronomers proposed it was a fragment of a planet torn apart by tidal forces in another star system. Others suggested a hydrogen iceberg, a nitrogen iceberg, a shard of frozen gas. The proposals got increasingly exotic because the simple explanations did not fit, and then it left, and we lost the chance to study it further. 3I Atlas is also strange. Its colour changed from red to green, or seemed to, depending on which observations you trust. Asteroids do not usually do that. Colour comes from surface composition. A change in colour suggests a change in composition, which suggests the surface is not uniform. Maybe it rotates and different sides reflect different wavelengths. Maybe it is outgassing lightly, and the coma is altering the observed spectrum. Maybe it is something else entirely. We do not know because we have not gotten close enough to resolve it. R2 fits the pattern in a different way. It is not interstellar. It is solar system native, probably from the Oort cloud. But it hid in the sun's glare and emerged only after perihelion, demonstrating how easily we can miss things even in our own backyard. If R2 can hide, so can others. How many long-period comets pass through the inner solar system undetected every year? We do not know. We only see the ones that brighten enough, that stay visible long enough, that cross our detection thresholds. The rest are ghosts. Is there a pattern? Maybe. The optimistic interpretation is that we're getting better at seeing the universe as it really is, full of transient visitors, debris flows, and unexpected arrivals. The pessimistic interpretation is that the rate of arrivals is increasing and we are not prepared. The realistic interpretation is probably somewhere in between. We are seeing more because we are looking harder, but we are also discovering that the baseline rate of cosmic traffic is higher than we thought. The solar system is not a quiet neighbourhood. It is a highway, and we are just now installing traffic cameras. Next, we're going to look at the institutions that manage this traffic, the data pipelines, the bottlenecks, and the silences that make people suspicious. Part 9. Institutions, silence, and the information life cycle. Let me walk you through how discovery becomes public knowledge. An observer, professional or amateur, spots something unusual. A moving object, a brightening source, a transient event. They record the position, the time, the magnitude. They check whether it is already known. If it is not, they report it. Where do they report it? To the Minor Planet Center, the MPC, operated by the International Astronomical Union. The MPC is the clearinghouse for observations of asteroids, comets, and other small bodies. It collects data from observers worldwide, verifies it, and issues circulars when something new is confirmed. But verification takes time. A single observation is not enough. You need multiple observations to confirm the object is real, to rule out instrumental artifacts, to calculate a preliminary orbit. That means waiting for other observers to point their telescopes at the same patch of sky and confirm the sighting. If the object is faint, if it is near the detection limit, if it is moving fast, confirmation can take days, sometimes longer. Once confirmed, the MPC assigns a provisional designation and publishes an electronic circular. The data is public, available to anyone, but it is raw data. Orbital elements, position vectors, magnitude estimates. It is not a press release. It is not a headline. It is a technical document for astronomers. The general public does not read MPC circulars. They read news articles, and news articles come later, if at all. Meanwhile, other institutions refine the orbit. The Jet Propulsion Laboratory, JPL, runs Horizons, a system that calculates precise trajectories for solar system objects. As more observations come in, the orbit solution improves, uncertainties shrink, predictions become more reliable. If the object is potentially hazardous, if its orbit brings it close to Earth, JPL flags it. The Center for Near-Earth Object Studies, CNEOS, evaluates the risk. If the risk is high enough, NASA issues a statement. If the risk is low, they might not. For R2, the process played out like this. Vladimir Bezugli, an amateur astronomer, spotted the object in SWAN data on September 11, 2025. He reported it. Other observers confirmed it optically. The MPC issued a circular designating it C/2025 R2. JPL calculated the orbit. CNEOS evaluated it. The conclusion was no threat. The closest approach would be 0.26 astronomical units, far enough to be safe. No press release, no public warning, just a technical update buried in a database. And that is where the silence begins. Not because anyone is hiding anything, not because there is a conspiracy, but because the system is designed for risk mitigation, not public engagement. If an object is not a threat, it does not get headlines, and if it does not get headlines, most people never hear about it. R2 was mentioned in a few astronomy outlets, a few space news websites. It made the astronomy picture of the day on September 18th. But it did not trend on social media. It did not dominate the news cycle. It was just another comet, one of dozens discovered every year. Contrast this with 3i Atlas. Interstellar, mysterious, colour-changing, weird acceleration. That is headline material. That is the kind of story that gets picked up by mainstream media, shared on social platforms, discussed in comment threads. It does not matter that 3i Atlas is harmless, that its closest approach is 1.8 astronomical units, that it poses no risk. It matters that it is interesting. And interesting sells. This creates a vacuum. When institutions do not provide detailed, accessible updates, when the information lifecycle is slow and technical, when the gap between discovery and public awareness stretches to weeks or months, speculation fills the space. Social media users notice the gaps. They ask questions. Why are we not hearing more about this? Why is the coverage so sparse? Is something being hidden? And in the absence of official answers, unofficial answers emerge. Theories, conspiracies, rumours. Vladimir Bezugli's discovery of R2 is instructive here. He is not a professional astronomer. He does not work for a space agency. He is an amateur who knows how to analyse swan data. The fact that he found the comet before the professional surveys did is not a failure of the professionals. It is a reminder that the detection network is porous, that non-traditional paths matter, that sometimes the most important observations come from unexpected places. But it also raises questions. If an amateur can find a comet that the professional surveys missed, what else are we missing? How many objects pass through the inner solar system undetected because they are in the wrong place at the wrong time? Because the surveys are looking elsewhere? Because the sky's too bright, or the weather is bad, or the instrument is down for maintenance? We do not know. We cannot know. That is the problem. The information life cycle is slow by design. Verification prevents false positives. Caution prevents panic. But caution also creates gaps, and gaps create doubt. When people do not trust the institutions to tell them the truth, they look for alternative sources, and alternative sources are not always reliable. Next, we're going to do a triage of the wildcard ideas, the conspiratorial claims, the fringe theories. We're going to separate what is worth considering from what is not. Part 10. Wildcards and conspiracies. Let me be clear. People will say that R2 is not a natural object. They will say it is a probe, a craft, an engineered device sent by someone or something to observe us. They will say the trajectory is too convenient, the timing too perfect, the outbursts too controlled. They will say NASA knows more than it is telling us, that the images are suppressed, that the real data is classified. They will say this is a message, a warning, a test, and they will believe it. So let us triage. Let us take these claims one by one and see which ones deserve any attention at all. Claim 1. R2 is an artificial object. Is it physically possible? In principle, yes. Any sufficiently advanced civilization could build a spacecraft that mimics a comet. They could coat it in ice to create a coma when heated. They could program it to outburst on schedule. They could engineer the trajectory to pass close to Earth. It is possible, but it is not simple, and it leaves traces. If R2 were artificial, we would expect anomalies. Spectroscopy would show unusual compositions, elements or molecules that do not fit natural comet chemistry. The nucleus would have structures, geometric shapes, regularities that natural objects lack. The trajectory would show fine control, tiny adjustments inconsistent with outgassing, and there would be electromagnetic emissions, radio signals, infrared signatures, something indicating active systems. We have not seen any of that. The spectrum looks like a normal comet. The coma is consistent with sublimating ice. The trajectory follows gravitational dynamics. There is no signal. Occam's razor says the simplest explanation is usually correct. R2 looks like a comet because it is a comet. Invoking artificial origins requires adding assumptions, adding complexity, adding actors with unknown motives and unknown capabilities. It is possible, but it is not necessary. And in science, we do not invoke unnecessary explanations. Claim 2. The images are being suppressed. Are we seeing everything? Almost certainly not. Professional observatories do not publish every image they take. They process data, they calibrate, they filter noise, they select the best frames. Some data is proprietary, reserved for the research teams who propose the observations. Some data is low quality, not worth releasing. But suppression implies intent, a coordinated effort to hide information. And that requires a level of coordination that is difficult to achieve. Observatories are scattered globally. They operate independently. Amateur astronomers have their own equipment. If something dramatic were visible, someone would post it. The fact that we have not seen dramatic images suggests there are no dramatic images to see, not that someone is hiding them. Claim 3. The trajectory is manipulated. Could an external force be steering R2? If you mean aliens, then we are back to claim 1. If you mean natural forces, then yes. Outgassing creates non-gravitational accelerations. Comets are not ballistic. They push themselves around by venting gas. R2 as outburst. which means it is venting. That affects the trajectory. JPL models include non-gravitational forces. They account for outgassing. The trajectory predictions are not perfect, but they are good. If the comet were under active control, we would see deviations from the models that could not be explained by outgassing. We have not. Claim 4. This is harmless but symbolic. Some people argue that even if R2 is safe, even if it will not hit us, its arrival is meaningful, a sign, a portent, a synchronicity. This is not a scientific claim, it is a philosophical or spiritual claim. Science can tell you the orbit, the composition, the probability of impact. It cannot tell you whether the universe is sending you a message. That is outside the domain of empirical inquiry. If you find meaning in the arrival of a comet, that is your choice. But do not confuse personal meaning with physical risk. Now, are there any claims worth examining more carefully? Yes. 1. The possibility of fragmentation and debris hazards is real. It is not conspiracy. It is physics. If R2 fragments, if it sheds pieces that diverge from the parent trajectory, those pieces could create a hazard. Not an impact hazard, probably, but a debris hazard, a micrometeoroid flux, a satellite threat. That is worth monitoring. That is worth preparing for. It is speculative, but it is grounded in what we know about comet behaviour. The triage matrix looks like this. Artificial origin, not feasible without evidence. Image suppression, unlikely given the distributed nature of observation. Trajectory manipulation, no evidence beyond natural outgassing. Symbolic meaning, not scientific. Fragmentation debris, plausible and worth tracking. Speculation is fun. It is human nature to see patterns, to imagine agency, to fill gaps with stories. But we should always be ready to test those stories against data. And when the data does not support the story, we should have the discipline to discard the story and move on. Next, we are going to shift gears. We are going to look at other recent science headlines, starting with neuroscience, because the brain is also a detection system, and it also has blind spots. Part 11. Neuroscience. UCSF finds protein slowing brain aging. In August 2025, researchers at the University of California, San Francisco published findings on a protein that appears to regulate brain aging. The protein, identified in experiments with aged mice, seems to act as a brake on neural plasticity. When the researchers blocked this protein, the aged mice showed improvements in memory and learning. Their neurons fired more reliably. Their synaptic connections strengthened. In some measures, their brains behaved like younger brains. The experiment was straightforward. Take old mice, identify the protein that accumulates with age, block its activity using a drug or genetic manipulation, then test whether behavior improves. The results were promising. Aged mice that received the treatment performed better on memory tasks. They navigated mazes faster. They recognized objects more reliably. The effect was measurable, repeatable, and statistically significant. But this is mouse work. Mice are not humans. Mouse brains are simpler, smaller, organized differently. What works in a mouse does not always work in a human. The history of neuroscience is littered with treatments that cured mice, but failed in clinical trials. Alzheimer's has been cured in mice dozens of times. Humans are still waiting, so caution is necessary. The findings are exciting, but they are preliminary. The implications, if they translate, are enormous. Cognitive decline is one of the most feared aspects of aging. Memory loss, difficulty learning, slowed processing, these still independence and identity. If blocking a single protein could slow or reverse that decline, the impact would be profound, not just for individuals, but for societies dealing with aging populations. The economic cost of dementia is measured in trillions of dollars globally. A treatment that delays onset by even a few years would save vast resources and vast suffering. But there are complications. Proteins do not act in isolation. They are part of networks, cascades, feedback loops. Blocking one protein might have downstream effects, might disrupt other systems. The aged mice in the study did not show obvious side effects, but the observation period was short. Long-term effects are unknown, and humans are more complex. We live longer, we accumulate more damage, we have more comorbidities. A treatment that works cleanly in a mouse might interact unpredictably with human biology. Here is the metaphor. The brain is a detection system. It scans the environment, processes signals, forms memories, makes predictions. When it works well, it catches details, it adapts, it learns. When it ages, it loses sensitivity. Signals get weaker, noise creeps in, patterns become harder to see. The protein identified by UCSF researchers seems to be part of that degradation process. By blocking it, the researchers restored some of the brain's youthful sensitivity. Now think about our astronomical detection systems. Telescopes scan the sky, process signals, catalogue objects, predict trajectories. When they work well, they catch faint comets, they track asteroids, they warn of hazards. But the systems also degrade. Instruments age, sensors drift, calibration becomes less precise, data pipelines get cluttered with noise, and over time, we start missing things we used to catch. The parallel is not perfect, but it is instructive. Both systems, brains and telescopes, are built to detect patterns in noisy environments. Both degrade over time. Both can be restored, at least partially through intervention. For brains, it might be a protein blocker. For telescopes, it might be recalibration, sensor replacement, upgraded algorithms. The principle is the same. Vigilance requires maintenance. The UCSF study is a reminder that hidden mechanisms control what we see and what we miss. Sometimes the mechanism is biological, a protein that accumulates with age. Sometimes it is technological, a sensor that drifts out of alignment. Sometimes it is institutional, a survey schedule that leaves gaps. The solution is always the same. Identify the mechanism, understand how it works, then intervene to restore function. Next, we're going to look at another neuroscience headline, this one about Alzheimer's, because the pattern of sensational claims and cautious realities is worth understanding. Part 12. Alzheimer's Reversal Headline. October 2025 brought another wave of headlines. Alzheimer's reversed in mice. The articles were breathless. The social media posts were hopeful. The reality was more complicated. Researchers had tested a new intervention, possibly vascular restoration, possibly amyloid clearance, possibly protein regulation. The details varied depending on which study you were reading, but the theme was consistent. Aged mice with cognitive deficits showed improvement after treatment. Their brains cleared plaques. Their memory performance increased. In some measures, the pathology reversed. This is not the first time. Alzheimer's research has produced dozens of promising mouse studies over the past 2 decades. Vaccines that clear amyloid, drugs that reduce tau tangles, gene therapies that restore synaptic function. In mice, these interventions work. In humans, most of them fail. The translation gap is enormous. Mouse models of Alzheimer's do not fully replicate the human disease. Mice do not live long enough to develop the full spectrum of pathology. Their brains are simpler, their immune systems are different, their metabolism is faster. A treatment that works in a 6-month mouse study might fail in a 10-year human trial. Sample sizes matter. Mouse studies often use dozens of animals. Human trials need thousands of participants. Duration matters. Mouse studies run for months. Human trials run for years. Side effects matter. A drug that is safe in mice might be toxic in humans. Efficacy matters. A treatment that improves memory by 20% in mice might only improve it by 5% in humans. And 5% might not be clinically meaningful. The Newsweek summary, like many popular science articles, emphasized the positive. Reversal, breakthrough, hope, those words sell. But the primary sources, the actual research papers, are more cautious. They use words like preliminary, limited, requires further study. They acknowledge the translation challenges. They do not claim victory. They claim progress. Here is the problem. Complicated science becomes sensational headlines. Nuance is lost. Uncertainty is erased. The gap between what the researchers actually found and what the public believes they found grows wider. And when the treatment eventually fails in humans, when the clinical trial comes back negative, the public feels betrayed. They were promised a cure. They got another disappointment. Trust erodes. This pattern is not unique to Alzheimer's research. It happens in every field where the stakes are high and the science is complex. Cancer research, climate science, infectious disease, and yes, astronomy. When a new comet is discovered, the headlines talk about spectacular displays, once-in-a-lifetime events, naked-eye visibility. The reality is often dimmer, more uncertain, more dependent on variables we cannot control. Comets fade, they fragment, they disappoint, and the public, expecting a spectacle, feels let down. The lesson is skepticism, not cynicism, skepticism. When you see a headline claiming a breakthrough, read the primary source, check the sample size, look for caveats, ask what the researchers actually measured and what they inferred, ask what the limitations are, ask what happens next. Most of the time, the answer is more research needed, and that is fine. That is how science works. But it is not how headlines work. Headlines need certainty. Science deals in probabilities. The parallel to R2 is this. The comet is real. The observations are real. The orbit calculations are real. But the predictions, the brightness forecasts, the fragmentation scenarios, those are all probabilities. We do not know what will happen. We know what might happen, with varying degrees of likelihood. And the responsible thing to do is present those likelihoods clearly, without inflating them, without deflating them, without turning them into clickbait. Next, we shift to artificial intelligence, another domain where hype and reality diverge, but also a domain where real capabilities are changing how we detect cosmic threats. Part 13, AI, October 2025, Model and Tool Releases and Ethical Push. October 2025 saw several announcements in artificial intelligence. New models, new tools, new capabilities. Open source releases that push the frontier of what machine learning can do. Foundation models with improved reasoning, better context handling, faster inference. Companies and research labs unveiled systems that can process longer contexts, maintain coherence across complex reasoning chains, generate code more reliably, and interface with multiple modalities simultaneously. The pace of development is relentless. What seemed impossible 2 years ago is now routine. What seems routine today will be obsolete in 2 years. The acceleration is real, measurable, and shows no signs of slowing. And alongside the technical progress, an ethical push. Initiatives aimed at aligning AI development with human values, launched at global forums, backed by researchers and policymakers. The details vary, but the theme is consistent. AI is powerful, AI is accelerating, and we need to make sure it is aligned with what we actually want. Not just what we think we want, but what we truly value when consequences become real. The question is not just what AI can do, but what it should do, and who gets to decide. These are not abstract philosophical questions. They are urgent practical concerns. As AI systems become more capable, more autonomous, more integrated into critical infrastructure, the stakes rise. A mistake in medical diagnostics can kill. A mistake in traffic control can cause accidents. A mistake in astronomical detection can leave us blind to incoming threats. In astronomy, AI is already embedded in the data pipelines. This is not speculative. This is current practice. Automated anomaly detection scans survey images looking for transient events. Machine learning algorithms classify objects, distinguishing asteroids from stars, comets from galaxies, supernovae from variable stars. The classifications happen in milliseconds. A human would take minutes or hours to do the same work. Algorithms refine orbits, taking sets of position measurements and calculating trajectories. They predict future positions, estimate uncertainties, flag objects whose orbits bring them close to Earth. They flag potential hazards, objects that might pose collision risks, that might require follow-up observations, that might need to be added to watch lists. The volume of data is too large for humans to process manually. Modern wide-field surveys generate terabytes of data per night. Each image contains millions of sources. Each source must be measured, catalogued, cross-referenced with existing databases. Transient events, things that appear or disappear or change brightness, must be identified and flagged. The Vera Rubin Observatory, when it comes fully online, will image the entire visible sky every few nights. It will detect billions of objects. Tens of thousands of those will be moving, changing, transient. No human team could process that volume. We need AI to sift through it, to find the signals buried in the noise. Without AI, modern astronomy would drown in its own success, overwhelmed by the sheer quantity of information pouring in from telescopes every night. But AI is not infallible. It makes mistakes. It flags false positives, objects that look like hazards but are not. A cosmic ray hits the detector, leaving a bright streak. The AI sees a fast-moving object. It flags it as a potential asteroid. Follow-up observations show nothing. The object was never there. It was an artifact, a glitch, a phantom, or the AI misclassifies. A distant supernova brightens gradually. The light curve looks like a variable star. The AI assigns it to the wrong category. Days pass before a human notices the error and reclassifies it. By then, the optimal observation window is closed. Critical data has been missed. It misses real signals, especially if they are unusual, if they do not match the training data. Machine learning systems learn from examples. You show the system thousands of asteroids, and it learns what asteroids look like. You show it thousands of comets, and it learns what comets look like. But what happens when something arrives that does not look like the training examples? What happens when an object has properties that fall outside the distribution the AI was trained on? The system might flag it as noise, as an artifact, as something to be ignored. Or it might misclassify it, putting it in the wrong category, sending it down the wrong pipeline. Either way, the signal is lost, and it can amplify biases. If the training set is biased towards certain types of objects, the AI will be biased too. Suppose most of the training data consists of objects discovered by optical surveys in certain parts of the sky, at certain times of year, under certain observing conditions. The AI learns that pattern. It learns that asteroids usually have certain brightness ranges, certain colours, certain motion rates. Then an object arrives that deviates from the pattern. Maybe it is darker than usual, lower albedo, reflecting less sunlight. Maybe it is moving faster or slower than expected. Maybe it arrived from an unusual direction. The AI, trained on the biased sample, does not recognize it. It filters it out. It will catch what it was trained to catch and miss everything else. There is also the noise flood problem. As AI gets better at detecting anomalies, it generates more alerts. This sounds like a good thing. More detections mean better coverage, fewer missed objects. But more alerts mean more follow-up observations. More follow-up means more telescope time, more human effort, more resources. Telescopes are expensive. Time on a major observatory costs thousands of dollars per hour. You cannot follow up every alert. You have to prioritize. You have to decide which objects are worth the investment and which are not. If the false positive rate is high, the system gets overwhelmed. Astronomers spend all their time chasing ghosts and miss the real threats. Balancing sensitivity and specificity is hard. Sensitivity is the ability to detect real signals. Specificity is the ability to reject false signals. You want both to be high, but in practice there is a trade-off. Increase sensitivity, and you catch more real objects but also more false positives. Increase specificity, and you reject more false positives but also miss more real objects. The sweet spot, where you catch most real threats without triggering too many false alarms, is narrow and constantly shifting. It depends on the data quality, the observing conditions, the characteristics of the objects you're looking for. It requires constant tuning, constant feedback, constant human oversight. Hypothetical scenario. An AI analysing comet brightness data flags a weird spike in R2's light curve. The comet has been brightening steadily since discovery, consistent with increasing solar heating as it approaches. Then, on October 15th, the brightness jumps suddenly. Not by a huge amount, maybe half a magnitude, but the jump is sharp, abrupt. not the gradual change the models predict. It looks like an outburst, but the timing is odd. The pattern does not match previous outbursts. Previous outbursts happened near perihelion, when solar heating was maximum. This one is happening weeks later, when the comet is moving away from the sun. That is unusual. Is it real? Is it an instrumental artifact? Maybe the telescope had a tracking error. Maybe atmospheric conditions changed. Maybe the calibration was off. Or is it something unexpected, something physical happening to the comet? A fragment ejection, a collision with a meteoroid, a pocket of volatiles suddenly exposed and venting explosively. The AI cannot tell. It does not understand physics. It does not have models of comet behaviour. It just compares the data to patterns it has seen before. This pattern is unusual, so it flags the anomaly and passes it to a human. The human astronomer receives the alert. It is one of dozens that day. She looks at the data, sees the spike, checks other instruments. Has anyone else observed R2 recently? Are there independent measurements that confirm the brightness change? She searches the databases. Nothing. The spike appears in only one dataset. That is suspicious. Artifacts usually appear in single datasets. Real events usually show up in multiple datasets, unless the timing was unlucky, and only one telescope happened to be looking at the right time. She checks the observing log. Were there any issues that night? Any problems with the telescope, the detector, the weather? The log shows scattered clouds, variable seeing, nothing unusual. She looks at images from before and after the spike. The comet looks normal. No obvious structural changes. No new fragments. No dramatic brightening in subsequent observations. The spike seems to have been temporary, if it was real at all. Maybe it was noise. Maybe it was real but brief, lasting only a few minutes, not long enough to be confirmed by other observers. She makes a decision. The evidence is ambiguous. The spike could be real, but it is probably an artifact. Without confirmation, without additional data, issuing an alert would be premature. It would consume resources, trigger follow-up observations, mobilize other astronomers, and if the spike turns out to be nothing, it wastes everyone's time. She decides not to issue an alert. The anomaly is logged in the database, marked as unconfirmed and forgotten. She moves on to the next alert. The system continues. But what if it was real? What if the spike indicated fragmentation, and pieces are now diverging from the parent trajectory? The human decision, made under uncertainty with incomplete data, might have missed something important. Fragments take time to separate. In the first hours or days they are close to the parent, difficult to resolve even with high-resolution imaging. By the time they are far enough apart to be seen as distinct objects, they might have diverged enough to pose separate threats, and the AI, which caught the anomaly, gets ignored. Not because the human was negligent. She followed protocol, she evaluated the evidence. She made a reasonable call, but reasonable calls made under uncertainty are sometimes wrong. Over time, humans learn to distrust the AI's alerts because most of them are false positives. This is alert fatigue, a well-documented phenomenon in medical diagnostics, aviation safety, nuclear power plant operations, and now astronomy. When alarms sound too often without consequence, people stop responding with urgency. They tune out. They develop heuristics to filter the noise. Maybe I will only respond to alerts with confidence scores above 90%. Maybe I will only follow up if multiple instruments flag the same object. Maybe I will deprioritize alerts that come from older telescopes with known calibration issues. These heuristics are rational. They save time. They focus resources on the most promising targets. But sometimes, those heuristics filter out the signal too. The real threat, the one that actually matters, might have a confidence score of 85%. It might be flagged by only one instrument, because only one happened to be looking at the right time. It might come from an older telescope that, despite its age, still caught something real. And when that alert arrives, it gets dismissed as noise. The pattern recognition that helps humans cope with information overload also blinds them to genuine anomalies. This is the challenge of human-AI collaboration. Neither is perfect. AI is fast but dumb. It processes vast amounts of data in seconds, identifies patterns that humans would take hours to see, never. Gets tired, never loses focus. But it does not understand context. It does not have intuition. It cannot reason about whether an anomaly makes physical sense. Humans are slow but smart. They understand physics. They have intuition. They can reason about causality and plausibility. But they are limited by attention, by fatigue, by cognitive biases. They can only look at a small subset of the data. They miss things that happen outside their focus. The system works best when they complement each other, when the AI handles volume and the human handles judgment. The AI scans everything, flags anything unusual, and passes it to humans for evaluation. The humans examine the flagged items, apply context and intuition, and decide what is real and what is noise. But it requires trust, calibration, feedback loops. The humans must trust that the AI is not missing critical signals. The AI must be calibrated so that its alerts are informative, not overwhelming. And there must be feedback loops, mechanisms for humans to tell the AI when it got something right or wrong, so the system can learn and improve. And it requires that humans remain vigilant, that they do not become complacent, that they do not assume the AI will catch everything. The moment humans start treating AI as infallible, as a perfect detector that never misses anything, is the moment the system becomes dangerous, because AI is not infallible. It is a tool, powerful but limited, and it requires human oversight to function correctly. The danger is not that AI will fail. The danger is that humans will trust it too much and stop paying attention. And when they stop paying attention, the things that slip through the cracks multiply. Detection is no longer just hardware. It is not just about building bigger telescopes with better mirrors and more sensitive detectors. It is software. It is algorithms. It is decision trees and neural networks and statistical thresholds. It is the rules we write to distinguish signal from noise, the models we build to predict trajectories, the pipelines we construct to process data. And all of that is built by humans, trained on data selected by humans, deployed in context defined by humans. The biases, the gaps, the blind spots, those are human creations. They are choices, sometimes deliberate, sometimes unconscious, embedded in the systems we build. AI can help us see further, but it cannot fix the fundamental problem. We are looking for patterns in a universe that does not care whether we find them. The universe does not optimize for our detection. It does not make things easy. Objects arrive from inconvenient angles at inconvenient times with inconvenient properties that do not match our training data. They hide in the sun's glare. They arrive during bad weather. They fragment unpredictably, and our detection systems, human and artificial, must adapt to that reality or fail. The challenge is not just building better tools, it is building better collaboration between tools and the people who use them. Next, we're going to use another neuroscience study, this one about spatial memory and aging, as a metaphor for how detection systems degrade over time. Part 14. Instrument and Sensor Degradation Metaphor, Stanford Spatial Memory and Aging. On October 3, 2025, researchers at Stanford published findings on spatial memory decline in aging brains. They studied neurons in the hippocampus, the brain region responsible for forming cognitive maps of the environment. These are not abstract maps. They are neural representations of physical space, built from experience, refined through repetition. In young animals, these neurons fire reliably when the animal occupies a specific location. The firing pattern is precise, consistent, reproducible. Cell A fires when the animal is in corner 1. Cell B fires when it is in corner 2. The pattern creates a mental map, a neural coordinate system that allows the animal to know where it is and how to get where it wants to go. But in age animals, the neurons fire less reliably. Cell A might fire in corner 1, or it might fire in corner 2, or it might not fire at all. The map becomes fuzzy. Locations blur together. The animal still knows it is somewhere, but the somewhere is imprecise. Navigation becomes harder. The animal hesitates. It doubles back. It takes wrong turns. It still reaches the goal eventually, but the path is inefficient, uncertain, marked by errors that a younger animal would not make. The study traced the mechanism behind this decline. Certain proteins accumulate with age, binding to synaptic receptors and reducing plasticity. Synaptic plasticity is the ability of connections between neurons to strengthen or weaken based on experience. It is the physical basis of learning and memory. When plasticity declines, neurons lose their ability to update the map, to correct errors, to incorporate new information. The result is a degraded representation of space. The map is there, but it is outdated, imprecise, unreliable. The animal still navigates, but less accurately. It makes more mistakes. It takes longer to find goals. The decline is gradual, subtle at first but measurable. Over time it compounds, the errors accumulate, the map decays. This finding is more than just neuroscience. It is a metaphor for every detection system we have ever built. Telescope systems age in exactly the same way. Instruments start sharp, precise, calibrated to detect the faintest signals. But over time, they degrade. Optical alignment drifts. The mirrors that focus starlight are mounted on mechanical structures that expand and contract with temperature. Over months and years, tiny shifts accumulate. The focus softens, the image spreads. Light that should converge on a single pixel spreads across several. The point spread function, the mathematical description of how a telescope renders a point source, broadens. Resolution declines, mirrors accumulate dust. Even in the best observatories, even in sealed environments, particulates settle on the optical surfaces. Dust scatters light, reducing the amount that reaches the detector. Worse, some telescopes are exposed to the elements. Wind carries grit. Temperature changes cause condensation. Over time, the mirror surface oxidizes. Aluminum coatings, applied to create reflective surfaces, degrade. Reflectivity drops from 98% to 95% to 90%. Each percentage point lost means fewer photons captured, fainter objects missed. Eventually, the mirror must be stripped and re-illuminized, a process that takes weeks and costs hundreds of thousands of dollars. Sensors develop defects. Charge-coupled devices, the silicon chips that convert photons into electrons, accumulate damage from cosmic rays. High-energy particles slam into the silicon lattice, knocking atoms out of place, creating hot pixels that register false signals. Dead pixels appear, zones where photons arrive but no signal is recorded. Noise patterns emerge, systematic errors that must be subtracted during image processing. The detector still works, but its dynamic range shrinks. Its sensitivity declines. Objects at the limit of detection, the ones that produce only a handful of photons per exposure, drop below the noise floor. They vanish. Calibration becomes less precise. Every telescope needs regular calibration to convert raw detector counts into meaningful measurements. You point the telescope at stars of known brightness, measure the signal, and build a calibration curve. But calibration drifts. The detector response changes. The optical throughput changes. The atmosphere changes. If you do not recalibrate frequently, your measurements become unreliable. An object you think is magnitude 6 might actually be magnitude 5.8 or 6.2. That uncertainty propagates. Brightness estimates become less trustworthy. Orbital predictions that depend on brightness become less accurate. The error bars grow. The images get fuzzier. The detection threshold rises. Objects that used to be visible, that used to produce clear, confident detections, now hover at the edge of statistical significance. Is that a comet or a noise spike? Is that a moving object or a cosmic ray hit? The ambiguity increases. Observers become less confident. Follow-up observations are required, but telescope time is scarce. If every marginal detection requires confirmation, the system bogs down. The queue grows. Objects move on before they can be confirmed. We miss them. Maintenance helps, but only to a point. Mirrors can be cleaned. Dust can be removed with careful wiping or blown off with compressed air, but cleaning introduces risk. A scratch, a smudge, a residue left behind, these can make things worse. Re-illuminizing restores reflectivity, but it requires removing the mirror, shipping it to a coating facility, waiting weeks for the process to complete, then reinstalling and realigning. During that time, the telescope is offline. Observations stop. The survey pauses. Objects that would have been detected during that window are missed entirely. Sensors can be replaced. New charge-coupled devices with better quantum efficiency, lower noise, wider dynamic range, these are available. But replacement is expensive. A single detector can cost millions of dollars. Installation requires precision. The detector must be cooled to cryogenic temperatures to reduce thermal noise. The cooling system must be maintained. Leaks happen, pumps fail, systems go offline, and even with a new detector, the rest of the optical train is still aging. The telescope is only as good as its weakest component. Calibration can be redone. In principle, you recalibrate every night, using standard stars, checking the 0 point, measuring the extinction. In practice, clouds interfere. Schedules slip. Automated pipelines use old calibration files. The drift goes unnoticed until someone checks and realizes the measurements are off. By then, weeks or months of data might be compromised. Orbits calculated from that data carry the error forward, objects are mislocated, predictions fail, but maintenance requires resources, time, money, expertise, budgets are finite, funding agencies prioritize new missions over maintaining old ones. Once a telescope is built and operational, the excitement fades. The headlines move on. The scientists who designed it retire. The engineers who built it move to other projects. The institution is left with an aging system and a shrinking budget. Maintenance gets deferred. Upgrades get postponed. The system degrades faster than it is repaired. Entropy wins. The Stanford study shows that even biological systems, which are self-repairing, which regenerate constantly, still degrade with age. Neurons lose function despite the brain's ability to grow new synapses, to prune unused connections, to reorganize neural networks. The hippocampus is one of the few brain regions where new neurons are born throughout life. Neurogenesis continues into old age. Yet even with this regenerative capacity, spatial memory declines. The new neurons do not fully compensate for the accumulated damage. Synapses weaken, proteins accumulate, maps become unreliable. The degradation is slower than it would be without regeneration, but it is still inevitable. Our astronomical instruments do not have this luxury. They are not self-repairing. They do not regenerate. Once damage occurs, it persists until someone intervenes. An intervention is slow, expensive, often incomplete. A mirror cleaned today will accumulate dust tomorrow. A sensor replaced today will accumulate hot pixels next year. A calibration done today will drift next month. The degradation is relentless. The pace is faster than biological systems because there is no repair mechanism built in. And when the instruments degrade, we miss things. R2 is a case study in how detection failures happen. The comet was discovered late because it was in a geometric blind spot hidden in the sun's glare. But blind spots are not always geometric. Sometimes they are instrumental. A faint comet at the limit of detection might be visible to a new telescope with a freshly coated mirror and a pristine detector. The same comet, observed months later with the same telescope after dust has accumulated and pixels have died, might be invisible. The object has not changed. The telescope has. And because the telescope has degraded, the detection fails. The same object, observed with the same technique, gives different results depending on the state of the instrument. This is not a hypothetical problem, it happens. Survey telescopes detect fewer objects in their later years than in their early years, even though the sky has not changed. The decline is attributed to aging hardware, degraded optics, sensor failures. And if we do not account for that, if we do not regularly test and recalibrate, if we do not track the instrument performance over time, we start missing things we used to catch. We do not realize we are missing them because they never appear in the data. They are ghosts, invisible, undetected, unknown. There is also data fatigue, a different kind of degradation. Telescopes generate enormous volumes of data. Modern wide-field surveys produce petabytes per year. Every image contains millions of pixels. Every pixel contains a measurement. Processing that data requires pipelines, automated software that identifies sources, measures positions, calculates magnitudes, cross-references catalogues, flags anomalies. The pipelines run continuously, ingesting new data, outputting results. But as the volume grows, the pipelines strain. Processing times increase, queues form, data gets backlogged. An image taken tonight might not be processed until tomorrow or next week. By the time an anomaly is flagged, by the time a human looks at it and decides it needs follow-up, the object has moved on. The observation window closes. We miss the chance to confirm, to refine the orbit, to assess the risk. Data storage is another bottleneck. Petabytes require infrastructure, hard drives, servers, cooling systems, redundancy, backup. All of this costs money. When budgets tighten, storage gets cut. Old data gets archived to slower media, tape drives that take hours to access. If you need to reprocess old images, if you need to search for a faint object that was missed the first time, you wait. You submit a request. You wait for the tape to be loaded, the data to be transferred, the processing to complete. Days pass, the object is gone. Vigilance requires maintenance, not just of hardware, but of software, of procedures, of institutional knowledge. Software has bugs. Pipelines have assumptions baked in. A threshold set 5 years ago might no longer be appropriate. The sky has changed. Light pollution has increased. Satellite. Constellations have multiplied. The number of streaks and flares in every image has exploded. The pipeline flags them as anomalies. The queue fills with false positives. Real anomalies get buried. Adjusting the threshold is not simple. Change it too much and you miss real objects. Change it too little, and the false positives continue. Someone has to monitor the pipeline, tweak the parameters, test the results. That someone needs expertise, experience, institutional knowledge. Astronomers retire, engineers move on. The people who designed the system, who understand its quirks, who know where the blind spots are, who remember why certain decisions were made, they leave. Documentation helps, but it is never complete. Subtleties get lost. New people come in. They learn the system, but they do not know it intimately. They do not have the intuition that comes from years of experience. Mistakes happen. A parameter is changed without understanding the downstream effects. A calibration file is updated incorrectly. An assumption is made that was previously challenged and rejected. The new team does not know the history. They repeat old errors. The system drifts away from optimal performance. Detection rates decline. No one notices until someone runs a retrospective analysis and discovers that the telescope is missing objects it should catch. The parallel to aging brains is exact. Both systems start sharp, degrade gradually, lose sensitivity, miss signals. Both require active maintenance to slow the decline. Both eventually fail despite our best efforts. The solution is the same. Refurbish, recalibrate, upgrade, replace aging components with new ones, train the next generation, document everything, build institutional memory, fight entropy at every level, knowing you cannot win permanently, but hoping you can delay the inevitable long enough to matter. The Stanford researchers showed that blocking the age-related proteins in mice restored some spatial memory function. The intervention did not make old mice young, it made them less old. It slowed the decline. It bought time. That is what maintenance does for telescopes. It does not restore them to factory condition. It slows the degradation. It buys time. Time to detect the next R2, the next unexpected visitor, the next object hiding in the glare or at the edge of sensitivity. Time is the resource that matters most. When systems fail, when detection lapses, when degradation wins, we lose time. And losing time means losing the chance to see what is coming before it arrives. Next, we're going to wrap up. We're going to talk about what comes next, what you should watch, what you should demand, and how this all connects to Apophis, the asteroid we know is coming in 2029. Part 15, Global Wrap, What to Watch Next and Mission Roadmap. If R2 is a wake-up call, here is where we go from here. The comet will make its closest approach on October 20th, 2025, at 0.26 astronomical units. That is 8 days away. Between now and then, here is what needs to happen. First, ephemeris updates. Track the trajectory. Refine the orbit. Watch for perturbations. Outgassing creates non-gravitational forces. If the comet outbursts again, if it vents asymmetrically, the trajectory will shift. Not by much, but maybe by enough. Keep measuring. Keep refining. Do not assume the current solution is final. Second, spectroscopy and radar. We need to know what R2 is made of. Spectroscopy tells us the composition of the coma, which gases are venting, which molecules are present. Radar, if the comet gets close enough, and if we point the right dishes at it, can resolve the nucleus, measure its size, detect rotation, maybe even see structure. This is not just scientific curiosity. Composition affects how the comet behaves. Volatile-rich nuclei outburst more. Structure affects fragmentation risk. If the nucleus is a rubble pile, loosely bound chunks held together by weak gravity, it might come apart. If it is a solid monolith, it will stay intact. We need to know which. Third, high-resolution imaging. Try to resolve the nucleus. Try to detect fragments. If R2 has split, if pieces are spreading, We need to see them now, while there is still time to track their trajectories. Fragments diverge slowly at first. The earlier we catch them, the better we can predict where they will go. Fourth, dust and debris monitoring. Look for trails. Look for ejection events. Look for meteoroid activity. Earth-based meteor cameras can detect particles entering the atmosphere. Satellite sensors can measure micrometeoroid flux. If R2 is shedding debris, if Earth is approaching a debris stream, we want warning. Even a few hours of warning is enough to put satellites into protective mode, to orient solar panels edge-on, to reduce cross-sectional area. Fifth, spacecraft hazard modelling. The International Space Station orbits at about 400 kilometres. Satellites occupy various altitudes, from low Earth orbit up to geosynchronous at 36,000 kilometres. All of them are potential targets. A dense meteoroid stream increases collision risk. The risk is still low, but low is relative. If the background flux is 1 particle per million cubic kilometres per hour, and a debris stream increases it to 10 particles per million cubic kilometres per hour, that is a 10-fold increase. Small numbers multiplied by large volumes and long exposure times add up. Model the flux, estimate the risk, prepare contingencies. Now, policy and systems. What should we demand from the institutions that are supposed to protect us? First, invest in solar ward surveillance. Most of our telescopes point away from the sun. That is natural. The sun is bright. It blinds sensors. But objects approaching from the sun's direction are invisible until they emerge. We need space-based telescopes positioned to watch the sun. Wardside, instruments that can see comets and asteroids in the glare. Soho's Swan proved this works. We need more instruments like it, dedicated to comet detection, covering more of the spectrum. Second, real-time public data pipelines. Transparency reduces the conspiracy vacuum. When observations are published immediately, when orbital solutions are updated in real time, when uncertainties are communicated clearly, trust increases. People do not need to speculate when the data is available. The Minor Planet Center and JPL already do this to some extent, but the interfaces are technical. We need public-facing dashboards, visualizations, plain language summaries. Make the data accessible. Make it understandable. Third, international coordination. Telescopes are scattered globally. Different time zones, different sky coverage, different capabilities. A network coordinated in real time can track objects continuously. When one telescope loses the object below the horizon, another picks it up. Alert protocols need to be standardized. If one observatory detects a potential hazard, how quickly does that information reach others? How quickly does it reach decision makers? Minutes matter, hours matter, days matter. Reflect on Apophis for contrast. Asteroid 99942. Apophis, diameter roughly 340 metres, will pass closer than geosynchronous satellites on April 13, 2029. That is less than 4 years away. We have known about Apophis since 2004. We have tracked it for 21 years. We know its orbit precisely. We know where it will be on April 13, 2029, down to the kilometre. We know it will not hit us. We know it will pass at about 31,000 kilometres, closer than some satellites, but still safe. We have time to prepare, to position instruments, to study it as it passes. Apophis is the predictable case, the one we saw coming, the one we get to watch in slow motion. R2 is the opposite. Unpredictable, late detection, uncertain orbit, unknown composition, possible fragmentation. R2 is the case that scares risk analysts, not because it will hit us, but because we almost did not see it, and there are others like it, others we have not seen, others we will not see until it's too late. The difference between Apophis and R2 is time. Apophis gave us decades. R2 gave us weeks. Time is the resource that matters most in cosmic defense. Time to observe, time to refine trajectories, time to evaluate options, time to act. When time runs out, options disappear. You are left watching, hoping, praying that the numbers hold, that the uncertainties do not swing the wrong way, that the fragments do not diverge into Earth-crossing orbits. Predictable large objects get attention. Apophis will be studied exhaustively. Every telescope will point at it. Every radar will ping it. We will learn more about asteroids in a single flyby than we have in decades of distant observation. That is good. But the risk comes from the objects we do not see coming. Small, fast, unanticipated. The radical unknowns, the ones that hide in the glare, that arrive from unexpected angles, that brighten suddenly after we have looked away. Those are the ones that will catch us off guard. The universe is not trying to kill us, but it is not trying to save us either. It is indifferent. Objects fly through space following gravity and momentum. Some of them cross our path. Most miss. Some hit. The distribution is statistical, random over short timescales, predictable over long timescales. We happen to live in a brief window where impacts are rare enough that civilization can exist, but common enough that we need to watch. The Chicxulub impactor that ended the dinosaurs struck 66 million years ago, 10 kilometers wide, traveling at 20 kilometers per second, releasing energy equivalent to billions of nuclear weapons. It dug a crater 200 kilometers across. It threw debris into the stratosphere. It darkened the skies. It ended an era. That could happen again. Not today, not tomorrow, not in our lifetimes, probably. But eventually. The question is whether we'll see it coming, whether we will have time to do anything about it, whether we will have built the systems, developed the technologies, trained the people, coordinated the institutions to mount a response, or whether we will be like the dinosaurs, unaware until the sky catches fire. R2 will not be that event. It is too small, too far, too well tracked. But it is a test of our detection systems, a test of our communication systems, a test of our ability to respond to uncertainty with rationality instead of panic. So far we are passing. The comet is being tracked, the orbit is being refined, the risk is being communicated. No one is panicking, no one should, but we should be paying attention, not to the spectacle, not to the headlines, not to the conspiracy theories or the doomers or the hype merchants. Pay attention to the gaps, the blind spots, the detection failures, the institutional bottlenecks, the things we miss because we are looking the wrong way at the wrong time with the wrong tools. Those are the lessons. Those are what matter. Watch the sky. Demand better survey systems. Question the narratives. Stay curious. Stay skeptical. The universe is full of wonders and full of hazards. Most of the time the wonders are safe to enjoy, but the hazards do not announce themselves. They do not wait for permission. They just arrive. And when they do, the only thing standing between us and extinction is the quality of our detection systems and the speed of our response. 8 days until closest approach. R2 is coming. We're watching. The numbers say we're safe, but numbers are not certainties. They're probabilities dressed in equations, and probabilities sometimes surprise us. That is why we watch. That is why we calculate. That is why we build telescopes and train astronomers and fund surveys and coordinate internationally. Because the alternative is not knowing, and not knowing is the only thing more dangerous than the objects themselves. The cosmos is not empty. It is full of debris, fragments, visitors, wanderers. Most pass harmlessly, some do not. R2 is a reminder that our neighbourhood is not quiet, that the traffic is real, that the risk is small but never zero, and that vigilance is not paranoia. It is survival. Keep watching.